In this next series of videos, we're going to find out how to compute the eigenvalues and eigenvectors of a matrix. So we're going to be given the matrix A and asked to figure out what multipliers can we find in there and for what directions do those multipliers apply. So the first thing is starting with the eigenvector-eigenvalue equation, and that is if I take some vector v and multiply it by A, v is an eigenvector if I get the same vector back but scaled by lambda. So that's our starting point. What we need to do is find out what is special or defines the lambda values. We're going to look for the eigenvalues first. It turns out those are easier to find as a first step. The first challenge we have here is that these whole things are vectors, right? This is a vector, this is a vector. However, the building blocks out front are not the same. One is a matrix, and one is a scalar. We'd like to be able to put those on the same playing field. So what we're going to do is multiply through by the identity matrix. We're going to take I times AV is equal to I times lambda V. Now, how does that change anything? Well, the identity matrix is like multiplying by 1. We have I times A is just equal to A again, so that's fine. So we're going to get back to AV on this side. But on the right side, we're not going to do that. We're going to call this lambda I times V. And so in some sense, we have an n by n matrix here. Well, in some sense, we do have. We now have n by n matrices on both sides multiplying our vector V. Before, we just kind of had this scalar, and that was hard to work with or cancel things out with. Now again, matrices, it doesn't mean that A is equal to lambda I. I wish that was the case. But what we can do is turn into a form that you'll have seen before. We're going to move all of this stuff to the other side. So we're going to get A times V minus lambda IV is equal to a 0 vector. Now we have a matrix times V minus, there is this grouping ability with matrix multiplication. We can gather those terms. If you think of its distributivity in reverse, V distributes into both of these things, or we can compact them together going the other direction. Okay, now here we bring in the big guns, bring back our linear algebra. For this to work, or for this to have any meaning, we have to have V be a non-zero vector. Right. If you think back to here, it doesn't make any sense to say, oh, the 0 vector gets scaled by some number. Well, I guess you could scale it by anything. It doesn't matter if it's the 0 vector. It only made sense if we had real directions for our V values here. All right. Well, then if that's the case, if V is a non-zero vector, then for this equation, V times this equals 0 means V is in the, ask yourself for a second, what is it in? What space related to this matrix is it in? It is in the kernel of A minus lambda I. Whatever this matrix is, V gets sent to 0. Plug that in, you scale it, it gets turned to 0. Well, what did we learn? Because, well, we learned a little while ago that since V is non-zero and it gets sent to 0, it's in the kernel, that means that the matrix A minus lambda I is not invertible. It's a square matrix which has not just the 0 value for its kernel, a 0 vector for its kernel, it takes other vectors to 0. If it's not invertible, then we have this lovely corollary that the determinant of A minus lambda I, I'm going to put this right up top here. This is the important thing. All this together means that the determinant of A minus lambda I must equal a 0 scalar value because determinants are scalar values. And that is something we can test for. Let's try that out on the matrix given here. The eigenvalue condition is that the determinant of this new matrix, A minus lambda I, has to equal 0. So how do we use this to find lambda? We're going to find lambda by building this A minus lambda I. And then we're going to take the determinant, set it equals 0. Find the determinant. and set equal to 0. All right, let's start with A minus lambda I. What does that look like? Well, the A matrix is easy. That's exactly the matrix we were given, 5, 3, -2, -2. Then minus lambda times the 2 by 2 identity matrix, like that. And what you see happens here, we can multiply that in. For the first time, we'll do this in gory detail. 5, 3, -2, minus lambda, 0, 0, lambda. And when we have addition and subtraction operations on matrices, we just do it to the matching elements. So this is 5, 3, -2, -2, except we have a minus lambda in the top left corner, a minus lambda in the bottom right corner, and no change at all to the other two terms, like so. That is the matrix A minus lambda I. It's our A matrix with minus lambdas added down the diagonal. All right, now we find the determinant of that A minus lambda I matrix. And that's easy enough here. It's this 2 by 2 matrix, so I have the 2 by 2 multiplied down the diagonal. So we're going to take, I'll do it in red here, this product minus that product, minus, and that one's easy, that's -6, like so. And what do you see when you expand this out? We get a quadratic in lambda. So we're going to get -10 plus 2 minus 5 plus 2 minus 5 minus 3 lambda. Double negative here, so plus lambda squared and plus 6. And we can tidy that up a little bit. That'll be lambda squared minus 3 lambda minus 4 overall. And then we set it equal to 0. We have to have this, not A, but this A with the lambdas down the diagonal subtracted, we have to have it have a determinant of 0. And that just means solve a quadratic. Okay, well, we can solve a quadratic. This looks at like factors of -4, lambda -4, and lambda +1. So you get -4 and -3. And so lambda equals 4 and lambda equals -1. Let's get the numbers here, 1 and 2, are the eigenvalues for A. 5, 3, -2, -2. And so what does that tell us? Well, so far, it tells us that A scales some direction unknown yet. Let's call it A direction by 4. And another direction, to be announced later, another direction by -1. So this matrix here doesn't look like it's hiding 4s and -1s particularly, but it will scale some directions by 4, one specific direction by 4, and some other direction by -1. To figure out what those directions are will be the next step. But before we do that, we're going to practice this determinant calculation on a 3 by 3 matrix just to get the experience on this side. So we're going to do another eigenvalue calculation on a larger matrix next.